Hi, my name's Megan, my partner's Martin, and we studied Thrackles, which are an interesting type of graph embedding. We hope that you'll learn something about graphs that can be characterized by this type of embedding. There's also a bonus question worth $1,000, so look out for that and email us your solution afterwards if you figure it out.
We spent a lot of time in class talking about planar graphs. As a reminder, a planar graph is one we can draw on the plane without any edges crossing. What if we consider graphs where edges can cross exactly once? There's a term for this kind of graph, a thrackle. Thrackles are embeddings of graphs in the plane such that every pair of edges meets exactly once. More specifically, a thrackle embedding of a graph is a function which maps each vertex to a point and each edge to a closed continuous line such that no line crosses itself. Each two lines intersect exactly once. If two vertices are connected by an edge, then the two vertices are mapped to the two endpoints of the image of the edge. And if two lines intersect, it's either at a common endpoint or at a shared interior point. A linear thrackle is a type of thrackle where edges are straight line segments. The pentagram, the X, and this third graph are linear thrackles. Notice that thrackles are simple graphs, but don't have to be connected. The graph on the right is the thrackle embedding of the 6 cycle. This is one of the classic depictions of a thrackle, which apparently is a Scottish term for a tangled up fishing line. In class, we studied extremal problems for planar graphs. For example, a planar graph with at least 3 vertices, so v is greater than or equal to 3, has at most 3v minus 6 edges. We can ask that same question for thrackles. What are the greatest and least possible number of edges? It's easy to prove that a thrackle with v vertices has at least 1/2 v edges, assuming we're not dealing with isolated vertices since every edge has 2. Finding the greatest possible number of edges is much trickier. John Conway was a very famous English mathematician, best known for Conway's Game of Life, but who contributed to many different fields of mathematics. In the late 1960s, he published a list of several unsolved problems with game-like elements and offered a beer to whoever could solve one. With no successes, after a while he upped the prize to $1,000, which was still available at his death in 2020. One of these unsolved problems is his thrackle conjecture. A thrackle cannot have more edges than vertices. Is E less than or equal to V? The bound is sharp. It has been proven that every cycle graph except for C4 has a thrackle embedding with the same number of edges and vertices. The star on the left is an example of this. The X is an example of the worst case thrackle. There are twice as many vertices as edges. Every edge is disconnected.
Paul Erdős is a late Hungarian mathematician who made some progress on the conjecture by proving it for linear thrackles. He observed that the number of edges is less than or equal to the number of vertices for thrackles where every edge is a straight line. Misha Pearls is a living mathematician who's a professor emeritus at the Hebrew University of Jerusalem. Pearls provides what is considered the most elegant proof of the observation. Consider a linear thrackle G and call V a pointed vertex if you can draw a line through V such that all edges incident to V are on the same side of the line, in other words, in the same half plane. For each pointed vertex V, delete the leftmost edge, where the leftmost edge is the first in the clockwise order, starting at the half plane around V, that's given by that line I just mentioned. See part A of the figure for a visualization. After deleting the leftmost edge incident to all pointed vertices, we should have deleted all edges. If not, then there must be some edge, UV, that is not leftmost at U nor V. See part B of the figure for a visualization of this. Suppose that some edge V prime U was leftmost at U, and some edge VU prime was leftmost at V. Then, the angle V prime UV is less than 180 degrees, and the angle UVU prime is also less than 180 degrees. If either of these are not the case, then the edge UV would be leftmost with respect to either U or V. You can convince yourself by looking at the graph that if V prime UV and UVU prime are both less than 180 degrees, then the edges V prime U and VU prime cannot intersect because they exist on opposite sides of UV. This contradicts the definition of a thrackle, which says that every pair of edges intersects exactly once. Take a look at part C of the figure, which demonstrates why this argument doesn't work for nonlinear thrackles. When we allow curved edges, any argument about angles goes out the window. So we've proven by contradiction that the number of edges is less than or equal to the number of vertices for linear Thrackles. Not quite good enough to win Conway's $1,000, though. So what if the conjecture is false? Can you think of a condition that a counterexample must satisfy? As a hint, try to think about what kinds of simple graphs have more edges than vertices. We'll pause for about 30 seconds to give you some time to think about this. A minimal counterexample must have some cycle. If not, it's a tree, and we know that the number of edges is less than the number of vertices for trees. But a cycle means that the number of edges equals the number of vertices, so there must be either another edge between nodes in the cycle, or multiple cycles that share a vertex to achieve the number of edges greater than the number of vertices. Graph B, the theta, demonstrates the prior, and graphs A and C, the dumbbell and the figure 8 respectively, demonstrate the latter. Note that these images describe the shape of the graphs, but there can be an arbitrary number of vertices between the ones drawn, for example, a length 3 path between the cycles in A. So if there's a counterexample of any of these types, then there will be a counterexample of all of these types. It is easy to see that there's a counterexample of type A if and only if there's a counterexample of type C, because you can add or remove the path connecting the cycles from the counterexample graph of one type to create a counterexample of the other type, since the length n path in A adds exactly n edges and n vertices to C, so the inequality between the number of edges and the number of vertices is not affected. There is also a counterexample of type B if and only if there is a counterexample of type C, by adding or removing the path at the point of connection between the cycles in C. Again, the length n path in B adds exactly n edges and n vertices to C. Note that the paths above and below the middle path in B must have more than 2 edges each in order to avoid creating multiple edges when collapsing the middle path. This can always be done because adding one edge to the outer path requires adding one vertex, so the inequality between the number of edges and the number of vertices is not affected.
While the Thrackle conjecture remains unproven, the upper bound on the number of edges has gotten lower and lower. In 1997, Lovash, Pak, and Szegedy published the first serious improvement on the upper bound of the number of edges. First, they show that every bipartite Thrackle is a planar graph, using Kuratowski's theorem. Without getting into the details, they show that every Thrackleable bipartite graph doesn't contain a subdivision of K5 or K33. They then use this to show that every Thrackle of n vertices has at most 2n minus 3 edges. This proof requires a good amount of work, but we can prove 2n minus 4 much more easily. By the definition of bipartite graphs, they can't have cycles of length 3, since no vertices within the same set are adjacent. Thus, every face of a bipartite planar graph is bound by 4 or more edges. We learned the handshaking lemma in class, the idea that in every finite graph, the number of vertices that touch an odd number of edges is even, following from the degree sum formula. There's an analogous handshaking lemma for faces. The sum of the edges around every face in a bipartite planar graph is half the total number of edges. Since every face is bound by 4 or more edges, for a graph with f faces and e edges, we have 4f is less than or equal to 2e. Euler's polyhedral formula says that the number of faces plus the number of edges minus the number of vertices equals 2. Combining this with the handshaking lemma for faces, we get 2 is less than or equal to e over 2 plus e minus v. Thus we have an upper bound on the number of edges for a bipartite planar graph, and therefore for Thrackles. For a Thrackle with e edges and v vertices, e is less than or equal to 2v minus 4. This upper bound has been progressively diminished over the years. The most recent result, by Fulek and Pak in 2017, shows that e for a Thrackle is at most 1.3984v. Furthermore, Pak proved that the methods used to improve this upper bound can't pass 1.375v. So the Thrackle conjecture will remain unproven without an exciting theoretical breakthrough, maybe by you. Conway's estate would owe you $1,000.